I want to welcome you to the lecture part of the Summer Science Saturday. You know, the big planets get all the attention. Today we're celebrating the smaller bodies in the solar system. This has been a good week with the flyby of Pluto by the New Horizons mission. It's been a good year. The Dawn mission is in orbit around Ceres, the biggest of the asteroids right now. And it's a good decade. Next year we'll be launching a spacecraft that is being designed and much of it built here at the U of A. And our three lectures this afternoon, one of them will be talking about Pluto, one about Ceres, and one about the OSIRIS-REx mission. My name's Tim Swindle. I'm the director of the Lunar and Planetary Laboratory here. I want to thank you, Dan. I want to welcome you, and in case you have been around the area and are wondering, yes, Maria Schuchart did find the same fabric store where I got the fabric for this shirt, and that is what the tablecloths are in the next room. But I didn't make my shirt. My wife did not make the shirt out of the tablecloths. So I want to welcome you. I also want to, after this, we'll be showing between talks, we'll have some slides about some other activities that we have going on. I'm not going to list all the names and dates, but just to let you know, in case you're interested, we have an evening lecture series during the fall. We have 3 lectures, one a month basically. We have a more low-key lecture series called Space Drafts at Borderlands Brewery that runs every 2 or 3 weeks. And so the schedule for that will show up here. And we have the Art of Planetary Science, a creation of our graduate students, where we have lots of artwork inspired by planetary science, or some of it is even actually plots of data, some is beautiful photographs. And I invite you to that. Those are all free. So the first talk this afternoon is going to be about Pluto and the Kuiper Belt in the big picture of the solar system by Professor Renu Malhotra. I'm not going to give a long introduction of where she got her degrees and stuff, but I want to mention 3 things about Renu. First, she is besides being a professor in the Department of Planetary Sciences here, she's also the director of the Theoretical Astrophysics program at the University of Arizona. So instead of running spacecraft or looking through telescopes, she thinks. She does calculations, that sort of thing. You might be wondering, why do we have people like that? The second thing to know about Renu is that she was the first one to figure out the significance of Pluto's orbit for the solar system, which is a big deal. And the third thing to know is that it's a big enough deal that this spring she was elected to the National Academy of Sciences, which is basically the highest honor an American scientist can have. So you're hearing straight from the source, really. So, Renu. Oh, and I forgot to mention one thing, as I messed up the microphone thing. We do have assistive listening devices if you need them. If you need one, contact Josh Sosa right here, and I see a hand over there.
Well, thank you all for coming. I should say a little bit about myself. In generations past, people like me, as Tim said, we don't send missions, we don't build instruments, we don't work in a lab. People like me would be the people who would be doing calculations and predicting where the planets are at what time, when the eclipses will happen, to scare some citizens. So calculations and keeping track of motions in the sky. That's what people like me would have been doing. But I'd say ever since a lot of data was collected and Johann Kepler figured out that the planets move in these elliptical orbits, and then Isaac Newton came up with his theory of gravitation, which tells us how or why the planets move the way they do. how the planets move, not why, how the planets move, under what forces. People like me have many more arenas for thinking. And we came to think about broader questions. So we know where the planets are, what kinds of orbits they move in. And then we started thinking about, or asking questions like, how did they get to be that way? Why are the planets so far apart? Why do the orbits have the shapes that they do? So in that sense, I'm living a life in the current times when we can actually get answers to questions like that, get meaning, find meaning about why the planets move the way they do, why do eclipses happen at the times that they do, how did this come about? So we have some partial answers now, and I'll tell you by the end of this hour, I hope you'll have a better understanding of how Pluto's orbit has really been, for the last 20 years, I'd say. We've recognized that it's the smoking gun, that's the way I can put it, for some dramatic events that shaped our solar system long ago. So Pluto was discovered in 1930. Some of you may know people who were around at the time of this discovery, or who learned more or heard it in the news for many decades after that. This planet was discovered by Flight Tombaugh over just up the street in Flagstaff, and these are the discovery images. You can see that it's conveniently marked by this arrow. There's that little Pluto, and it's moved relative to the background stars. This young man spotted this movement of this very faint spot in the sky, that this was a new planet that had not been known before. And there was something, over the decades, there were even more peculiar things that we learned about Pluto. And just this week, we've had New Horizons go by, do a very fast flyby of this planet, this small planet. And here's a nice picture that the New Horizons came up with as Pluto comes into focus. The higher and higher resolution images we've had of Pluto since 1930. You just saw that over the decades, the more detail that we've learned has come from, primarily more recently, from the Hubble Space Telescope. Many of these, prior to the New Horizons images you saw, were from the Hubble Space Telescope. And now we have this close-up, which shows Pluto as, this is the latest global image of Pluto, which shows that this is a planet which is reddish, which looks like another planet that's familiar to us. Anybody know what that other red planet is? Mars, right. So this is like a little Mars. It's about a third the size of Mars, about a sixth the size of Earth, not too shabby for a planet. And it looks like it has geology, it has craters and mountains and plains. So it's a little planet. And it's not alone. Since 1970, we've known that it has a large moon called Charon. Charon is about half the size of Pluto itself. And this is an image of both Pluto and Charon taken simultaneously with the New Horizons spacecraft just a couple of weeks ago. And in about 10 years ago, in 2005, we discovered two more moons, Nix and Hydra. These were discovered by the Hubble Space Telescope, actually in anticipation of the New Horizons mission. The Hubble telescope was used to do a very deep and more detailed study of the Pluto system, and these two new moons were discovered. And a few years later, another one was discovered, Kerberos, out there, and a year later, another one, Styx. So Pluto now is known to have 5 moons, and since this time, the last 3 years or so, while there have been more studies, we have not discovered any more moons. So Pluto has 5 moons. The sizes of these are, let's see, so Charon, I said, is about half the size of Pluto. Its diameter is about 1,200 kilometers. And the other moons are all around, have diameters of about 30 kilometers or so, roughly the size of the city of Tucson. Okay. These orbit Pluto in the orbital periods are about 1 week for Charon and about 5 weeks or so for the outermost one, Hydra. Hydra is an interesting beast. It's very not round. These other guys, we can't really tell what their shapes are. We can tell that they're not horribly elongated or out of round, but this Hydra looks like it's actually significantly elongated and has a very interesting or peculiar shape. We'll hopefully know a little more about these as we get more data back from New Horizons. So my talk is actually not going to be too heavy on the physical properties, the geology of these bodies. I'm going to tell you more about how they fit into this big, large-scale picture of the solar system that we have. So the Pluto moon system is actually very flat. These 5 moons have orbits that are almost totally coplanar, even more flat than the solar system as a whole. And not only that, this plane of the moon system of Pluto is tipped nearly 90 degrees to the plane of the solar system. Okay, so Pluto, there's Pluto's orbit there. New Horizons is just past Pluto. And so Pluto presents more or less a target as the spacecraft goes past or went through the solar system. And then we know that there's even more company for Pluto besides these 5 moons. In the space that Pluto orbits, here's an animation by Alex Parker. So since 1992, we've discovered that in that space that Pluto lives in, there are lots and lots of small bodies. And you can see this is those circles you see are the circles of the orbits of the outer planets, Jupiter, Saturn, Uranus, and Neptune. This outermost circle is Neptune. And that big dot that we started off with was Pluto, which was known, of course, prior to the 1990s. But since 1992, we've discovered many of these small bodies orbiting beyond the orbit of Neptune, roughly. And these are called, this region is now called the Kuiper Belt. And all of these collectively, each dot that you see comes up every time, at the time that it was discovered. Here's a marker for the time. So this is going forward from now. Here's Pluto, which is now slightly below the plane of the solar system, and it's going further down. So Pluto's orbit is actually quite tilted. And okay, so now we have more than 1,300 Kuiper Belt objects are known. Kuiper, incidentally, was the first director of the Lunar Planetary Laboratory. The building is named after him. And the reason he has the Kuiper Belt named for him is not accepted by everybody. The Europeans like to call this Kuiper Belt the Edgeworth Kuiper Belt. Edgeworth was a British astronomer, thinker, who imagined that beyond Neptune's orbit, there ought to be some leftover remnants of the materials that went into making the planets, and that they should still be there as small bodies. And so most Europeans, or papers that you might run into from the Europeans, they will call it the Edgeworth Kuiper Belt. So the nomenclature here isn't entirely settled. Now, New Horizons has gone past Pluto, and in the future, it's sometime in 2019 or so, it's expected that it will pass by, it will target its trajectory to pass close to one of these small Kuiper Belt objects, and one of the potential ones, it hasn't been decided yet exactly which one it would be. Possibly this is the one. It's currently its name is simply this telephone number, 2014 MU69. This is an object that was discovered last year, and it's being tracked to figure out its orbit well enough to be able to target New Horizons, to get close enough to it and get pictures and learn more about it. Why do we care about small bodies in the solar system? Well, they're very interesting to planetary scientists because we think that they're the remnants of, or the leftovers of the building blocks of the solar system. Everything that went into making the planets, these are the leftovers, and so they have, they hold clues to the formation and the development of the planets and the solar system as a whole. And we know also there are almost practical reasons for being interested in these. We know that they have hit the planets in the past. We see scars of small bodies having hit the moon and the other planets in the impact craters. You go up north in Arizona, there's Meteor Crater. That's one of these small bodies that has hit the Earth not too far in the past. So these are potentially a hazard to mankind and to life on Earth, but they're also a possible space resource. Once mankind gets off the Earth and we have common, hopefully, possibly, space flight for humans, these can be a source of resources for people to use as they travel through space. So, there are many reasons to learn, to keep studying these objects and learning more about them. So here's what we have for the small bodies in the solar system, the overall architecture of the solar system. Going out from the sun, we know the terrestrial planets are very close in that little gap you see there that I haven't marked anything in. That's where Mercury, Venus, Earth, and Mars live. And then we have the asteroid belt. So this is a cartoon I drew by hand. And then we have Jupiter, Saturn, Uranus, and Neptune at those scaled distances from the sun. So Jupiter is about 5 times farther from the sun than Earth is. So Earth is just about there. And there's Jupiter 5 times farther out. Saturn is 10 times farther out. Uranus is about 20 times farther out. And Neptune is about 30 times farther out than Earth is, than where we are from the sun. And then beyond that, we have this great big Kuiper Belt, which is an analog of the asteroid belt, but it's bigger by about a factor of 10 in extent. It's also kind of fatter. These Kuiper Belt objects, their orbits take them in and out, up and down from the mean plane of the solar system. And in between the planets, where the planets live, here these outer planets, and in here the inner planets, we have these stragglers called the near-Earth objects. Some of you may have learned about those earlier today up on the 5th floor. Comets that come through every once in a while. Actually, the Kuiper Belt, we think, is a source of some of the comets that we see in the sky. And then in here, there are these stragglers called the centaurs, which are Kuiper Belt objects that have drifted out. And they hang around these big planets, crossing the orbits of the big planets for a few million years before they get thrown inward or outward. And so they don't spend very much time, and that's why their density is very low. So when I think about the distinct neighborhoods in the solar system, I think of the inner solar system and the outer solar system, outward of roughly Jupiter. In the inner solar system, we have the terrestrial planets and the asteroids and the near-Earth objects. In the outer solar system, we have these giant planets, the Kuiper Belt, and then these stragglers. So you can think of these centaurs as more or less the analog of the near-Earth objects in the inner solar system. The centaurs are the near-planet objects that hang around in very chaotic orbits, and mostly they end up hitting Jupiter or hitting one of these planets or getting ejected out of the solar system. Every once in a while, some of these can enter the can get scattered into the inner solar system, and we see them as what we call Jupiter family comets or the short period comets. Oh, and I should say there's a very big part of the solar system that we don't see. We have not directly seen, but we've seen pieces of it. That's called the Oort cloud. The entire solar system is surrounded by the spherical cloud of comets at very large distances, roughly halfway to the nearest stars. So we have this big giant cloud of comets surrounding the solar system, and then what we see as the long period or new comets, some of you may know, they come from this big cloud. So that's the hint that we have, these long period comets that come through every once in a while. Things like Hale-Bopp, the big, very spectacular comets that we see that are called the new comets. So they've been seen for the first time. They come to us from this Oort cloud. This is an artist's concept of what the solar system might look like if you were out to maybe 4 or 5 times the distance of Neptune. If you were sitting way out there at about 200 or 400 astronomical units, you'd see the Kuiper Belt as the biggest, shiniest structure The Kuiper Belt also has a lot of dust in it, so it would look, the dust would shine and would look bright in a belt like this. And you can see that Pluto's orbit, which is shown here, straddles more or less the entire breadth of the Kuiper Belt. The inner edge is near Neptune, a little bit inside of Neptune, and its aphelion, its largest distance from the sun, is out at the outer edge of the Kuiper Belt. And Pluto is possibly the largest member of the Kuiper Belt. We know from New Horizons now its exact size, and it's clearly as big as the other Kuiper Belt objects, the biggest Kuiper Belt objects that we have seen. Question there? Yes?
Why is the orbit of Pluto so different?
It's so different from the planets. You'll get the answer to that in a moment. Okay, that's going to be the main purpose of my talk, to explain why Pluto is the way it is. So here's Pluto. Pluto's orbit is tilted to the plane of the solar system by about 17 degrees. And there's something else about orbits that we like to measure. How do we measure an orbit? The shape of an orbit. So the sine major axis is what is the average distance from the sun. So the orbits typically are elliptical, not circular. So the size of the orbit, so if you take the largest diameter, half of that is called the sine major axis, so that's also the average distance from the sun. So Earth's orbit is about 93 million miles, its orbit radius, or its semi-major axis. And this distance is also known as 1 astronomical unit. So in planetary science, we use this as a unit of distance. So when I say that Jupiter is about 5 times farther from the sun than Earth is, I can say that Jupiter's orbit radius is 5 astronomical units. Eccentricity is a measure of how out of round the orbit is. So a circle would have an eccentricity of 0. A very skinny, a very squashed ellipse like this, very, very elliptical orbit, would have an eccentricity which is close to 1. Okay? Actually, when you get to 1, you get what's called a parabola. And beyond 1, bigger than 1, would be an orbit that's not even closed. It's a hyperbola. And that would be an orbit where, for example, comets can look like that. Their orbits can look hyperbolic, where they come in and they go out. They look like they don't even stick around the sun. They actually do. They're just extremely skinny orbits. And Pluto has an orbit eccentricity, which is about 25%. So somewhere in between these two circles that you see, or these two ellipses that you see here. So here, so we say that Pluto is eccentric. It's tilted to the plane of the solar system. And here's Pluto's orbit traced out with a top-down view. And you can see that its smallest distance from the sun, its perihelion, is inside that of Neptune's orbit. And its aphelion goes out there. That's the biggest, the largest, the furthest it gets from the sun. It goes out to about 50 astronomical units. So Neptune is at about 30. Okay, so Pluto's orbit is elliptical. It has an ellipticity or eccentricity of about 25%, and it crosses the orbit of Neptune. So when it was first discovered and its orbit was figured out, initial speculations were that this might be an escaped moon of Neptune, that it crosses the orbit of Neptune, and maybe at some point in the past, it used to be orbiting Neptune, and some catastrophic event allowed it to escape the gravity of Neptune. And that is actually, over the years, we figured out that that is pretty impossible to do based on physics. The gravity of Neptune, if there's a moon of Neptune, to get it out of Neptune's gravity is pretty much impossible, or highly improbable, I should say. It's almost impossible. The gravity well is so deep that it's like a cage. Moons of Neptune just have to stay there. It's really hard to get them out. So that idea wasn't very fruitful, let's say. So Pluto's orbit is eccentric, but it never actually collides with Neptune, and the reason for that is quite interesting. If we go into a frame that's co-rotating with Neptune's orbit around the sun, imagine being on a merry-go-round that's spinning at the same rate as Neptune is, then Neptune would be nearly stationary in this rotating frame. So here's Neptune in this rotating frame. It's nearly stationary. It's not exactly stationary because Neptune's orbit is also slightly elliptical. And so in this frame that's spinning at a constant rate, Neptune would actually jiggle a little bit. Okay? So in this frame, Pluto carves out a path like this. Okay, so when it goes, let's start Pluto at aphelion. Half an orbit later, Pluto is at perihelion, closest distance to the sun, closer to the sun than Neptune is, but it's far away. In angle, it's really far away, so it never collides with Neptune. And over long times, this where this perihelion occurs relative to Neptune drifts and drifts back and forth and back and forth and back and forth. So that's an oscillation that happens because of the peculiarities of gravity. So I'll show you that. It's a celestial dance called orbital resonance. And here's an animation of that. Pluto completes 2 turns around the sun for every 3 turns that Neptune makes. And because of this exact period ratio of Pluto and Neptune, they can maintain the relative angles between the longitudes where Pluto and Neptune are. Pluto is never, or Neptune is never in this region when Pluto is interior to Neptune's orbit. So Neptune would always be somewhere around here or there when Pluto gets close enough to the sun to cross Neptune's orbit. Okay, so what are these? How does a resonance like that get maintained? So resonances arise from gravity. Any gravitational mass we know warps space. Einstein taught us that. Any gravitational mass warps the fabric of space itself. So around any planet, the gravitational field has this kind of, we visualize it like in a picture like this, that the gravitational field is bent and warping space like so. And so you might also make an analogy to these toys that you see in malls where you throw in a coin and it spins around this well, and after a while your coin will go into the pocket there. But if you spin your coin with enough momentum, it may not fall in. It will keep going and go out. And comets follow orbits like that. They don't fall into that well. Moons of planets sit inside. They orbit well inside that well. They have just enough angular momentum that they stick around orbits like that, stay in stable orbits like that. But when you have many planets, okay, so when there are many planets, these waves in space, in the fabric of space, that the planet's orbits or the planet's gravity creates in interplanetary space, when we have the gravity of many planets acting all together, superposed all together, we get these waves in interplanetary space. And this allows for many, many interesting kinds of orbits. We actually use this, in a sense, we use this to send spacecraft out to large distances, like in the outer solar system. So an orbital resonance is one of these waves in space. And so one important thing to understand is that small bodies, which have very little mass, so the small bodies don't create too much of a warp in space, they actually can trace these structures and how these structures came to be in the solar system. And this is, I like to think of it as a flotsam that might track a wreckage of an ocean liner gets transported around the oceans due to the flows of ocean water and ocean currents. And so these small bodies in the solar system actually trace these warps in space that are created by the gravity, the superposed gravity of all the planets. And so now if we take a close look at the orbits in the Kuiper Belt, what we see, so remember I told you how we measure orbits in terms of their semi-major axis, how big the orbit is, half of the largest radius, and how eccentric the orbit is, how out of round. So a circular orbit would be at 0 eccentricity, a very elliptical orbit would be way up there. If we take all these 1,300 Kuiper Belt objects that we've discovered and measure their orbit, their eccentricities, and their semi-major axes, and put them on a graph like this, we see that they don't form a uniform distribution. Each dot here is a Kuiper Belt object with its particular semi-major axis and its eccentricity. We see that there are these clumps, and you can see I've marked here the places where there are these orbital resonances with Neptune. So Neptune is right here at a semi-major axis of 30 astronomical units and a nearly circular orbit, nearly zero eccentricity. Pluto, incidentally, is just about here. It has a semi-major axis of near 40 and an eccentricity of about 25%. So just about here is where Pluto would lie in this graph. And all these other Kuiper Belt objects live here. And you can see this big clump at this resonance that Pluto lives in, this 3-to-2 resonance. And all of these Kuiper Belt objects, we now even call them Plutinos, after like little Plutos. So these are these clumps of Kuiper Belt objects that lie in resonant orbits with Pluto. And the Plutinos form the biggest clump that we've discovered so far. You should know that our discoveries are really peter out at large distances because these objects get very faint. Okay, so there's a whole lot of what we call observational incompleteness. The farther out you go, we see a very small fraction of what's actually out there. Okay, so why are these Kuiper Belt objects piled up in these resonant orbits, resonant and eccentric orbits? So the question is that, well, the problem, as planetary scientists would pose it, is that the problem is the following, that it's not possible to grow small planets, even small planets, in eccentric orbits. When two little pieces of mass come together and they're moving in slightly different eccentric orbits in the same region of space, they come together, they hit each other with very high velocity. Okay, so they tend to break rather than accrete. And so to make these planets in these eccentric resonant orbits is very hard. It's pretty near impossible to do. So we conclude that they must have formed in near circular orbits, and something happened subsequent to their formation that led them to be shepherded into these resonant orbits. And so remember, when we first discovered Pluto, the initial idea was that it might be an escaped moon of Neptune because it crosses the orbit of Neptune. And that theory was abandoned fairly quickly. The newer theory is that Neptune migrated outward and it shepherded many Kuiper Belt objects into these eccentric resonant orbits. So that's the answer to your question, sir. And how did this happen? So this is called planet migration theory. And the idea is that the giant planets, when the planets had formed, there were still lots of leftovers of planetary building blocks lying around. And this is a cartoon picture. Please don't take it too literally. I've drawn little dots here for what we think of as the large amount of leftovers that were dominating the region beyond Neptune's orbit. But there are also these remnants crossing the orbits of the planets as well, in much greater numbers than they are today. So early in the history of the solar system, there was these gravitational effects of the planets, those warps that I mentioned in space that the planets create. They disturb these leftovers, they cause them to scatter, and over time, during the scattering process and cleaning out the solar system, if you like, cleaning out the space between the planets then spread themselves out. They drift relative to each other, their orbits drift. So imagine this is the distance from the sun. Jupiter started out a little bit farther out, and today it is at 5 astronomical units, but it used to be a little bit farther out because of this exchange of energy and angular momentum during this cleanup process in the solar system. And Saturn and Uranus and Neptune also spread themselves out in the process of cleaning out these leftovers of the solar system. So this is what we mean by that the planetary orbits have migrated. And this is also the time and the process by which the Oort cloud was created. Some good fraction of these leftovers were scattered out into very large orbits, and then they were placed in what we can think of the Oort cloud as the attic of the solar system. Okay? All our old primordial stuff is sitting there, and occasionally we get a glimpse of it through these comets. Well, let's look at the small bodies in the inner solar system. In the asteroid belt, this is again semi-major axis, distance from the sun. Now we are very close in to the solar system, close into the sun, 2 astronomical units, just twice as far as the Earth is from the sun. This is the inner edge of the asteroid belt. The outer edge is somewhere near Jupiter is out there at about that distance. Earth is down here. Mars is about here. So we see that the asteroid belt is confined a little bit outside of Mars' orbit and a little bit inside of Jupiter's orbit. And we see these gaps. Can everybody see these big, giant gaps? This is just the number of asteroids at different semi-major axes. And you see that there's this big dip at this location of 2.5 times the Earth's distance from the sun. 5 halves, or 5 to 2. Sorry, that's not 5 halves. 2.8 astronomical units. These numbers here are actually the ratio. These are orbital resonances with Jupiter. So an asteroid over here makes 3 turns around the sun, while Jupiter makes 1 turn. Okay, so this is a 3-to-1 resonance with Jupiter, a 5-to-2 resonance, the 2-to-1 resonance. So at these resonant orbits, we see gaps, which is the opposite of what we see in the asteroid belt. Now, these gaps were discovered by an American astronomer named Daniel Kirkwood. I think he was in Indiana. He did his studies in Indiana, and he wrote a paper that there were these gaps in the asteroid belt. Now, there were about 100 asteroids that had been discovered by the mid-1800s. And by looking at the distribution of the orbits of these asteroids, he noticed that there were missing asteroids at these places where the orbital periods were in these small integer ratios to Jupiter. So these are now called the Kirkwood gaps, and they were understood. The reason that asteroids were missing there, the reason turns out to be something called dynamical chaos. Remember those waves I mentioned in space, the way space is warped because of the superposed gravity of different planets? It turns out that at these resonant orbits, the gravity of multiple planets makes those waves really strong. You can think of it that way. And it's like the waves are turbulent and the orbits are not stable. Okay? And the reason why, so we can ask this question then, why is it that there are gaps in the asteroid belt? Let me skip that. Why are these gaps in the asteroid belt, whereas in the Kuiper Belt there are pileups of Kuiper Belt objects at these resonances? So this is a very obvious question, and the answer to this is actually quite hard to give. The answer is our understanding of it is deeply rooted in very subtle mathematics of how gravity behaves. And the simple way to put it is that Jupiter is about 20 times more massive than Neptune is. Okay? So the way Jupiter's warps in space work, they're far stronger than those of Neptune. So it's like, imagine you have waves, little gentle waves that Neptune creates, whereas Jupiter creates these very big, violent waves that break and crash. Okay? So the orbits at the resonances of Jupiter, therefore, are not stable. They are these waves so asteroids can hang around there for a little bit, but eventually they get thrown out. And so these resonant orbits of Jupiter are unstable, whereas the resonant orbits of Neptune are stable. Okay, so those are more gentle waves where Kuiper Belt objects can stick around for long periods of time in very stable orbits. So asteroids then, any asteroids that get into these Kirkwood gaps, asteroids do continue to drift into these gaps. Very quickly, on timescales of hundreds of thousands of years, they get ejected. They get removed from those resonant orbits, and some of them come to us as meteorites. Okay, we see fragments of those that drop to Earth as meteorites. The near-Earth objects are fed from these Kirkwood gaps into near-Earth space through these resonances. Okay, so here's a problem that's been recognized only in the last few years. And that is that these Kirkwood gaps are actually larger than what can be accounted for by the magnitude of the waves, these resonant waves that Jupiter creates. Okay, if you look at how wide these Kirkwood gaps are, they're wider than what we can explain by by where Jupiter creates its resonances. And so it turns out that planet migration theory provides a very neat solution to these larger than expected gaps, because these resonances of Jupiter simply moved over time. Remember, I showed you that cartoon picture of the migration of the planets. Jupiter, we think, used to be slightly farther out than where it is today. So when Jupiter moved closer to the sun, these resonances they follow Jupiter. So they used to be a little bit farther out, and today they are where they are. So during that movement of the resonances, the gaps got wider. The gaps used to be a little farther out, and all of the asteroids, as these resonances moved, all of those asteroids got depleted. So that neatly explains why the resonances, the Kirkwood gaps, are bigger than we expect them to be. So now you can ask, okay, so we lost a lot of asteroids from these gaps. Where are those asteroids? Where did they go? Most of them, it turns out, if you throw an asteroid out of these Kirkwood gaps, most of them will hit the sun. In the last few years, we have space probes that have been studying the sun, close to the sun, and we've actually seen asteroids dropping into the sun, falling into the sun. They're called sun grazers, sun-grazing asteroids. So most asteroids actually hit the sun. Some escape into interstellar space. They escape the gravity of the sun and move off into interstellar space. And some some of them do hit the planets. We see scars of those. We can observe the signs of this, all the asteroids that were removed during this migration of the planets. We see scars of these on the rocky planets, on Mercury. There's Mars, and this is the moon. On the planets, the rocky planets that have preserved their surfaces from billions of years ago, these craters were made, we think, by these asteroids that were removed from the Kirkwood gaps as the planets migrated. And there are some subtle signatures of that. The sizes of the craters that we see, the ancient craters on the moon and Mars and on Mercury, the very ancient craters have a different size distribution than the younger craters. And so those the ancient craters match really well to what we think the size distribution was of these small bodies when the small bodies were very young, 4 billion years ago or so. In fact, some of these heavily cratered terrains on the moon and Mars and Mercury have been dated, actually mostly the moon, have been actually dated through lunar samples to about 4 gigayears old. Okay, so we have absolute ages of samples from the moon that these very heavily cratered terrains date back to about 4 gigayears ago. Even on Earth, we have fragments of ancient rocks. Here's an example where we find very ancient continental rocks in Australia, in what's called the Jack Hills region of Australia here on the western side. And these are little samples about 200 microns across. These are zircon crystals, which show these shock ages, that they were bombarded with, that rocks on Earth were bombarded with very high pressures at an age of about 4 gigayears ago. Okay, so we think that this age of 4 gigayears is dating a time of very heavy bombardment in the inner solar system, and we associate this with this migration and moving of the resonances in the asteroid belt that removed a lot of asteroids and threw them at the planets. So we think that this rearrangement of the planets happened about 4 billion years ago, and so of course, a lot of asteroids hit the planets at the time, but the happy thing is that this process decimated the asteroid belt and the Kuiper Belt. Okay, so while the Kuiper Belt and the asteroid belt used to be about 10 or 1,000, well, we think about 1,000 times more massive than they are today, all of that mass was removed. Most of that mass was removed, and only a little bit actually remains to tease us that there used to be an asteroid belt, a huge big asteroid belt, and a huge big Kuiper Belt back 4 gigayears ago. So now, because of this decimation of the small bodies early on, we now enjoy a relatively low flux of meteoroidal impacts in the inner solar system. So this brings me more or less to the end. Let me just summarize that Pluto has lots of company. We didn't know about this until about 10 years ago, these 5 moons. And we've been learning more and more about the Kuiper Belt and the Plutino component that accompanies Pluto in its orbit around the sun. There are hundreds of Plutinos and thousands and hundreds of thousands of Kuiper Belt objects there. Pluto's peculiar orbit is not so peculiar, given what we've learned about the Kuiper Belt. There are lots of Pluto-like orbits that are eccentric and resonant. And we think that Pluto's peculiar orbit is the smoking gun of this ancient planet migration. This ultimately led to the solar system we live in. It led to this rearrangement from a very compact orbital configuration of the giant planets to the more spread out configuration we have now, which makes the solar system far more stable. And these small bodies, which is the theme of this event today, the small bodies of the solar system allow us to learn some really big things about the history and the formation and the development of the solar system. So I'll stop here and I'll take questions.
Yeah, the microphone's on either side.
So why is the Oort cloud spherical and the rest of the solar system flatter?
Uh-huh. So I showed you how these small bodies get ejected out. It's all from the gravity of the giant planets. Once they get to very large orbits, if you scatter a small body out to a very large aphelion distance, you don't scatter it really to a big orbit. Its perihelion is still going to be near where it got scattered. But once the small body travels to many hundreds of astronomical units, there are other gravitational forces that act on it, mainly the nearby stars. Okay, so the nearby stars and the galaxy, the gravitational field of the galaxy becomes comparable or a good fraction similar to the gravitational field of the sun at many hundreds of astronomical units. So there, the gravity then torques this orbit and changes the angular momentum of this object so that its perihelion, so you have this object that was traveling on this very elliptical orbit. It went far out there in its orbit. The galaxy then torques it and turns that orbit into a circular orbit so that it does not come back to where it started. Okay, so now it's going to be this great big orbit which has a radius which is many hundreds, thousands of astronomical units, and its perihelion is no longer near the sun. Okay, so these elliptical orbits get turned into circular, very large circular orbits. Now, why you would think that they would still be more or less in the plane of the solar system, but the same reason, the same torquing by the galaxy also turns it, because the nearby stars don't know about the plane of the solar system. They go every which way. And so these orbits get torqued over time, over hundreds of millions of years. They get torqued into an isotropic distribution.
With all of this dynamic
Would you-
movement of small objects,
To use
why are there so few between Jupiter and Neptune? They're all either inside Jupiter or outside Neptune.
Right. So the orbits beyond Neptune are stable, long-term stable. Every now and then, some of those objects, they drift in and have a close-in, what planetary scientists call a close encounter with Neptune, and they get scattered into these orbits that are in between Jupiter and Neptune's orbit. Those orbits are highly unstable. That's where all these resonant effects are pile up on each other, and the orbits are turbulent or chaotic. We call them chaotic. Okay, so they don't spend much time there. So it's a time scale thing. So these orbits that are farther out are very stable, and objects that are there will stay there for long periods of time. But if they ever drift into somewhere between Neptune and Jupiter, they spend very little time there. So they come in and they very quickly pass through, and they might have a close encounter with Jupiter, which sends them out of the solar system, because Jupiter is just so massive, they get removed. Or Jupiter scatters them inward, and we see them as comets. But the comets then don't last very long because they get very close to the sun and sublimate and so forth. So you just don't spend much time there.
I've seen simulations of the migration of the planets where Neptune starts out as within the orbit of Uranus, and then it migrates out, and you did not have that. Has that been discounted?
Pretty much, yes. The details of this migration are still under study. It is possible that the planets themselves switched around, but there are a number of other subtle things about the way the orbital eccentricities of the planets behave relative to each other that discounts that particular simulation that you've seen, okay, where Uranus and Neptune switch around. It's not, we can almost completely rule out that kind of exchange.
Thank you. From your description about the planet migration, talking about Jupiter getting closer to the sun and the effect it had on the gaps in the asteroid belt, my tendency would be to think that Jupiter was more or less pushing on those objects as it moved in and therefore would compress those gaps. Why is that not the case?
So if imagine Jupiter is, well, where Jupiter is today, there's a gap at a certain distance, say the 3-to-1 resonance is at that 2.5 astronomical units. When Jupiter was farther out, that resonance would have been a little bit farther out. So so Jupiter would have created a gap at, let's say, 2.7 astronomical units. Okay, so Jupiter started out by making a gap at 2.7. As it moved inward, that gap was centered at 2.6 and 2.5, and so there's a gap. It does not push the asteroids into the gap; it actually removes them, right? Okay. There's a question here.
So basically, if something was to move into the previous place, it would stay there. It wouldn't be thrown off by the resonance. Like you said, it moved from 2.7 to 2.6 to 2.5. So if an object moved into the 2.7 area, it could stay there. And
If it were to move in later, it would stay there. Yes.
Okay.
Yeah.
And
But you'd
also-
have to have some mechanism to move it there from wherever it starts out with. It's not so easy to move asteroids around.
Yeah.
Right?
Yeah. Okay, and why is the solar system for the most part in a plane instead
Why
of
is it
random?
in a plane? Okay. So we think that the planetary system, or the solar system and other planetary systems, form out of a cloud of gas and dust, which used to be more or less spherical, but it had some angular momentum. Even a spherical mass has some angular momentum. We find these gas clouds in interstellar space. They have some small spin. So when they contract under gravity, and they might contract because there's some small fluctuation in density, maybe a fluctuation in temperature. If they get cooler for some reason, gravity can take over and make them contract. When they contract, their angular momentum is conserved, and they start spinning faster, okay, just like a figure skater who pulls in his or her arms, starts spinning faster. So if a big cloud of gas and dust that went into making the planets, the solar system, starts contracting, it's going to get flatter, okay, because its angular momentum is conserved. It's going to spin faster, and then if it spins faster, each individual particle is going to have more collisions. So imagine two particles colliding. On average, they're moving with some angular momentum like this. Two particles that collide will cancel their up and down motion and end up closer to the mean plane, to a plane that's normal to the overall angular momentum vector. Okay, so a gas cloud that contracts and there's lots of collisions going on inside will flatten out like a pizza. You start off with a ball of pizza, spin it, it flattens into a disk. And that's more or less how we think that's the reason why planetary systems seem to be more or less flat. We found hundreds of planetary systems. There's this Kepler, the Kepler spacecraft has found hundreds of planetary systems, and most of them are pretty flat, or within a few degrees, similar to the solar system flatness. There are other things that can happen later, like Pluto got kicked up into this inclination. I didn't actually go into explaining why Pluto's orbit is I explained to you why it's eccentric more or less. I didn't tell you why it got to be lifted out of the plane. it's the same resonances can also kick the orbits of small bodies out of the mean plane. And those kinds of things can happen to planets as well. If you have very big, super Jupiter kind of planets in a planetary system, even the planets can kick each other into somewhat inclined orbits relative to each other. So those processes are possible after the formation of the planetary system. And some systems might well have very inclined orbits or not be so flat. But so far, all the systems we've seen, most of the systems tend to, the majority of them look like they're pretty flat. They don't undergo a lot of kicking around of their orbital planes.
Is there any difference in composition between the Oort cloud objects and the Kuiper Belt objects?
We'll have to wait and see, won't we? We don't So we have some studies of what comets, Oort cloud comets, are made of when they come through, and we do spectroscopic studies and figure out the relative abundances of different chemical elements, chemical species, molecules in them. The Kuiper Belt, we have very little information about the chemical composition in detail of Kuiper Belt objects in their native places. We think that the short period comets that we see come from the Kuiper Belt. And so we can compare the compositions of long period comets and short period comets. So the long period ones, or the new comets, come from the Oort cloud, and the short period comets come from the Kuiper Belt. And we can look for differences there. We don't have good enough data to be able to tell a whole lot of differences, but maybe there's someone in the audience who knows more about this. There might be some subtle differences. There aren't any gross differences that we know. Okay, they're all made of ices. Water ice is a common common component. Methane ices, nitrogen ices are fairly common in both types of objects. So that's one reason I think that this picture holds that the Oort cloud was also made from the same region of space as the Kuiper Belt. The Oort cloud were these small bodies that were thrown out from the same region of the giant planets, the outer solar system. And the Kuiper Belt objects were also made from that same region of space.
Do you know where we can find any visual simulations of how you were describing the gravity waves that would create these resonances? Or is that like a really complicated simulation?
So those pictures I showed you, I'll confess, I just got them off the web just to provide you with a visual of those. So what the warps in space that multiple planets create, I actually have not seen anyone simulate those. If you're a crack programmer and can do that, come and see me. You can do that. Yeah. There was a question here, I think.
So with the difference between the Kuiper Belt objects and the Oort cloud objects, is it a matter of how much energy was introduced to throw them out that far, the Oort cloud, or do we not understand that?
Okay, so what's the difference between something getting thrown out to the Oort cloud versus thrown inward, maybe? Or okay, so it depends quite sensitively on exactly how a small body has that close encounter with a planet. You know, it's the way for example, New Horizons, the way New Horizons was launched and how its trajectory through the solar system. Yeah, here we go. This trajectory that New Horizons took, so here it was launched at Earth, right here, and then it went past in this inner, here you can see this, as it went past Jupiter, it actually had a close encounter with Jupiter. Okay, you can see that there's a very tiny change in its track. It got a little bit of a deflection from Jupiter. Not only did its path get changed, its direction got moved, angled a little bit, but Jupiter also gave it some acceleration. And exactly how we aimed New Horizons, we did that very carefully to get exactly the amount of acceleration and direction change that we wanted. Now, the natural bodies that have these close encounters with the planets, how exactly they do that encounter will determine how much they get deflected and how much acceleration they get. Okay? So the ones that come very close to Jupiter will get a huge big kick and might end up in the Oort cloud. The ones that have a very shallow encounter might end up, say, getting deflected inward. Okay. Was there a question there? Okay. Okay, one question over there in the back.
You mentioned that Jupiter orbit had come in. Do we expect it to be stable at this point in time, or continue to increase towards the sun?
Drift? No.
Yes.
So we think it's not. It's been more or less in its current orbit for something like 4 gigayears. There's been very little change. There is always some amount of change because some asteroids are still leaving the asteroid belt. We get them here as near-Earth asteroids, and we get meteorites. So these little masses that leave the asteroid belt, they're doing that under the influence of Jupiter. So every time there's an asteroid that leaves the asteroid belt, there's a little tiny, tiny effect on Jupiter. But the cumulative effect over the last 4 gigayears has been really, really small. And the reason we can know that is that that same thing that I was telling you about, how the gaps are bigger than we expect. If we look at Jupiter today, the gap that it creates, the inner edge of that gap, of the gap that Jupiter can create, matches very well with its current orbit. So if it had drifted, if it had continued to drift over the last 1 billion years, that we would have seen signs of that in the shapes of the Kirkwood gaps. Okay? So we think that Jupiter's orbit has not changed significantly in the last 4 gigayears or so. And the reason is there's not much mass left in the asteroid belt. All of that mass that got removed early on. So there's very little that's now drifting out of the asteroid belt. Okay?
In an animation I saw of Pluto and Charon, it showed them moving around like this to each other.
Tilted. The plane is tilted to the solar system plane. Yeah.
Well, not quite that. See, most moons move around the planet and the planet just goes its way. But Charon and Pluto, more like this.
I'm sorry.
Yeah, I think what
Yeah.
it means is that the common center of gravity is outside of Pluto.
Yes,
more
that's
like
right.
A binary planet system.
That's right.
Yeah,
yes.
exactly.
That is right, yes. So the center of gravity in the Pluto moon system is outside of the physical body of Pluto, right?
So how does that affect the outer moons?
Oh yes, it makes their orbits actually quite complicated. I showed you the orbital periods of the moons. They are between 1 week. Charon's orbit is about 6.4 days, and the longest orbit is 38 days. The outer moons are actually they are influenced by these resonances as well. So there are inter-moon resonances that are going on in Pluto, and the orbits seem to be actually chaotic. Okay? And it's quite a puzzle. There are some groups working to figure out how did these orbits come about. So it's a very interesting orbital system there. Right? So I think we should wrap it up, right? We have the next talk, which is we're already past that. Sorry, Shane.